this video, I'm going to be working example 1 from page 195 in your textbook. Example 1 on page 195 in your textbook. And this is what it says. A 5-meter ladder leans against a wall. The bottom of the ladder is 1.5 meters from the wall at time t equals 0 and slides away from the wall at a rate of 0.8 meters per second. Find the velocity of the top of the ladder at time t equals 1. So in this problem, we have a house and there is a ladder leaning against the wall and we're told that as it's leaning against the wall, the base of the ladder is sliding away at 0.8 meters per second. Now, this problem is a good example of a related rate problem. And what is going to be happening here is there's this relationship between the bottom of the ladder that's sliding away from the house and the top of the ladder, which hopefully you can intuitively tell that if the bottom of the ladder is going to be sliding away from the house, the top of the ladder is going to have to be sliding down. And so the question that we're asking is how these things are going to relate to one another, how fast the top of the ladder is going to have to move if the bottom of the ladder is moving. And I don't know if you've ever noticed this before, but whenever you lean something up against a wall and the bottom of it starts to slide out, then what you can see is that as it starts to slide out, even if the bottom, which it normally does, kind of strangely, the bottom seems to move at a constant speed as it slides out. But you'll notice that the top part that's coming down whenever something slides away from a wall actually begins to speed up as it falls down. And that's not just because of gravity, okay? There's a calculus element to it that makes that bottom part slide out faster, or excuse me, the top part begin to fall faster and faster as the bottom gets farther and farther away from the wall, even if the bottom is moving at a constant rate. Okay, so we want to talk about what is happening between these two things, how they're related to one another. And what's really important in a related rate problem is for you to be able to pull out information, okay? So whenever we start this, the first thing that they said was that the ladder was 5 meters. So we have this ladder that's leaning up against the wall, and it is 5 meters long. I'm going to call this side right here C, and I'm going to label it as being 5 meters. Then I want to look at this distance from the bottom of the ladder to the house. That distance is not as straightforward as it may appear when you read the problem. It says that the bottom of the ladder is 1.5 meters from the wall at time t equals 0. So this is when everything starts. At the very beginning of the problem, the ladder is 1.5 meters from the wall. But the question at hand is the velocity of the top of the ladder at time t equals 1. And so if we're going to use a related rate problem of what's happening when t equals 1, then we don't need to know the distance that the ladder was from the wall at time 0. We need to know how far the ladder is from the wall at time t1. Well, if it started off at 1.5 meters from the wall and it's moving at 0.8 meters per second, and we're asking the question of what is happening at time t equals 1 second, then that means that 1 second has elapsed from when the ladder was 1.5 meters from the wall. So in that time, if it's moving at 0.8 meters per second, we would multiply by 1 because 1 second has elapsed, and we would find that the ladder has moved by 0.8 meters, which means all in all, this distance that the ladder is from the wall that we're concerned with in the problem is a total of 2.3 meters. So I'm going to erase the rest of this, and here's the number that we're concerned with. Right now, at time t equals 1, which is what we're asking a question about. The ladder is 2.3 meters from the side of the house, and I'm going to call this distance down here A. Now, in a related rate problem, you're always going to have to come up with a formula. You are going to have to think of a formula on your own for how these different things are related to one another. And so the question right now is how this side C, this side A, and I'm going to call this side here B, which we don't know about right now. How are A, B, and C related to one another? What formula ties those three things in together? And hopefully you can see, because of the fact that we have a right triangle right here with sides A, B, and C, that the formula that's going to connect all of these sides together and how they have to relate to one another will be the Pythagorean theorem. So our magic formula in this case is going to be A squared plus B squared equals C squared. Now, along with these regular side lengths A, B, and C, we also need rates of change, related rates, because the bottom of this triangle right here, the distance that the ladder is away from the base of the house, is not staying the same. It's moving. It is changing. So what we need is a rate of change. We need the change in distance A with respect to, now this is the question, what is it in respect to? Well, what is elapsing as we move through this problem is that time is progressing. And so what we're going to talk about in this problem is what happens as time progresses. So we want to know how the bottom of the ladder, that distance, the bottom of the ladder to the side of the house is changing as time progresses. And so what we're looking for here is actually a change in distance A with respect to the change in time. Now this was given to us, and hopefully you notice that whenever you read the 0.8 meters per second. In the unit meters per second, you have a change in distance. That's the meters with respect to a change in time. That's seconds. So when you see something that has a rate of change to that, meters per second, degrees per minute, miles per hour, when you're working related rate problems and you see those different rates that have to have a unit of measurement and a unit of time, okay? Those are the things that are going to relate to one another. Then you're looking, that is a clue for you whenever you see meters per second, miles per hour, that there is a change in distance or angle or something else with respect to time. So those kind of combinations are clues to you that what you have is a rate. So this rate that we have right here, since it's how fast the ladder is sliding away from the wall, is a change in distance A with respect to time. So dA dt in this case is 0.8 meters per second. And we're told in the problem that it is constant. So it will constantly be moving out at 0.8 meters per second. Well, we have two other links here that we should question how they are changing with respect to time. dC dt. As time elapses, what is happening to this distance C right here? How is the time moving forward affecting what distance C is? And hopefully you can see that as this ladder slides down the wall, the actual length of the ladder, which is side C, is not going to be changing. If it's a 5-meter ladder and it's locked in place, when it begins to slide down the wall, it's not going to stretch or shrink at all. So as time elapses, it's actually going to have no effect on distance C whatsoever because it is the length of the ladder and the ladder is going to stay in place. So dC dt is actually 0. There will be no change in the length of the ladder as time progresses. dB dt, the change in distance B with respect to time, is what we're actually looking for in the problem. So dB dt is something that we're going to need to find. And hopefully you can see that it's going to be going down, so hopefully we will get out a negative number for dB dt, because if If side A is getting longer and the Pythagorean theorem is going to hold true, in order for side A squared plus side B squared to equal side C squared, if A gets longer, B is going to need to get shorter in order to make the Pythagorean theorem continue to work. And that's why we want to use the Pythagorean theorem as our related rate, because it's what's locking all of these three things together. It's how they're connected. So when you look at the Pythagorean theorem right now, in and of itself, we don't have any rates of change with the Pythagorean theorem. But what we can do in order to start to involve rates of change in the Pythagorean theorem is that we can actually take the derivative of the Pythagorean theorem. Now, remember that I said earlier that we're taking derivatives with respect to time. We want to know what's happening, how these changes are happening as time elapses. So we want to know as time progresses how these things are going to affect one another. So we'll take the derivative of the Pythagorean theorem with respect to t, or time. Now when I say that, you should notice that there are no t's in our formula. And so whenever the derivative that what we're trying to differentiate with respect to does not match the variables that we actually have in our formula, then we have to use implicit differentiation. So when I go to take the derivative with respect to t, I will take the derivative of a squared, and the derivative of a squared will be 2a, but since our variables don't match, we have to use implicit differentiation, so it will be 2a dA dt plus take the derivative of b squared with respect to t, and you will get 2b dB dt. Take the derivative of c squared with respect to time, and you will get 2c times the change in c with respect to the change in time. Now in this problem, we have 2's in front of every one of these. And so what I'm going to do in order to simplify is I'm just going to divide everything by 2, a perfectly legal move algebraically, because if we divide everything by 2, we haven't actually changed the value of the equation. So once we divide everything by 2, then all we have is that a times dA dt plus b times dB dt should equal c times dC dt. And at this point, we want to plug in. So we figured out rather, that at time t equals 1, the distance for A is 2.3 meters. So A is 2.3. The change in A with respect to time was given to us as 0.8 meters per second, plus B. We don't have a B right now, but there is a way for us to be able to find B. So let me change colors. I'll go to the red here, and we're looking for B. Remember, this triangle right here is connected through the Pythagorean theorem, which says that a squared plus b squared equals c squared. So if at time t equals 1, A is 2.3, and C is constantly 5, we can figure out what B will actually be. What will be the length of B at 1 second? So what we'll do is we'll use all of our other measurements for 1 second and figure out what B should be for 1 second. So if we plug in for A, 2.3 squared plus B squared equals 5 squared. Using the Pythagorean theorem in order to solve for B, we will get that B equals 4.44 if you round to the hundreds place, meters. So right now, at t equals 1, the distance for B is 4.44 meters. So 4.44 should go in for B. dB dt, if you remember, is what we are looking for. So we'll leave it as a variable. C was given to us as 5, and dC dt equals 0. And now we have an equation where we simply need to solve for dB dt. So if we multiply 2.3 and 0.8, we get 1.84 plus 4.44 times dB dt should equal 0. 5 times 0 there will give us 0. So now in order to solve this equation, we need to get dB dt by itself. So I'm going to subtract 1.84 from both sides. And I get 4.44 times dB dt is equal to negative 1.84. And that's a good sign because we know this answer should be negative. And now you can see that if we divide by 4.44 on both sides, in order to get dB dt alone, we're going to get a negative number because this negative divided by positive is going to be negative. So negative 1.84 divided by 4.44 gives us negative negative 0.41 meters per second. And notice here that I'm using meters per second because this is a rate of change. It's a change in the distance. There's our distance, meters, with respect to time. So there's our time in seconds.